Welcome to Introductory Chemistry with Dr. H. Today we're going to talk about how to name binary inorganic compounds. Naming compounds is an essential part of communicating in science, and there are systematic processes for accurately naming compounds to make sure that we can accurately translate a chemical formula to a name and names back to chemical formulas. The 0th step is knowing some key names and formulas, just like learning vocabulary in a foreign language, in which we must know both each word in English and in the language we're trying to learn. We've got to know some of these basic terms and how they relate to their formulas. So after that, the next step in the process is we need to make sure that we pick the right naming protocol by classifying the type of compound we're dealing with. There are different naming systems for different types of molecules. Finally, we need to apply that naming protocol. And so let's start this process at the 0th step by looking at the things that you need to memorize before you can name anything. I should mention now that the way to prepare for this is making a deck of flashcards. Flashcards are a very efficient way to memorize these names and formulas, and you'll be surprised how quickly you internalize these names in practice if you practice these a few times a week. So let's now switch and look at some of the things that you need to actually memorize. The first thing you're going to have to know, or you're going to have to be able to name ions. And so ions are atoms or groups of atoms that have a charge. Cations have a positive charge, anions have a negative charge. So if we look at this table of common ions, what you can see is that metals, things like lithium, magnesium, scandium, yttrium, metals adopt positive charges, so they're cations. And their names, the names for the ions, are the same as the name for the elements. So you can see that lithium cation there, the name for that ion is just lithium. On the other hand, the nonmetals, things like oxygen and sulfur, when they're in their ionic form, they're anions, and their name is changed by adding an IDE to the end of the name. So for example, oxygen becomes oxide, sulfur becomes sulfide, selenium becomes selenide, bromine becomes bromide. So those names aren't difficult to convert, but you have to know how to convert the element name to the ion name. And it's different when you're talking about metals, which are cations, and nonmetals, which become anions. Polyatomic ions are groups of atoms that hang together and have a distinct charge, and they function as a unit in molecules. The only way to know the names of polyatomic ions is to actually memorize their names and formulas. So there are many, many polyatomic ions, and I'm asking you to memorize just a few of the most common ones. And so you can see on this table of polyatomic ions, I've put an asterisk next to the ones that I think are super important to memorize. Things like the ammonium ion, the one cationic polyatomic ion that we're going to talk about. Ammonium has a positive 1 charge. You see their peroxide and cyanide. You see nitrite, which is NO2 minus, and nitrate, which is NO3 minus. There are somewhat systematic ways of naming some of these, but I think it's easiest just to memorize them. It's very quick and easy to memorize them, and once you start using them, they will just become permanent in your memory. So I'm not going to go through each of them because you have this table in front of you, and also it's something that is in most textbooks. Here are the common acids that, again, some of them have systematic naming, but I think it's just such a short list, it would be just as easy for you to memorize this list by using flashcards. I do want to draw your attention to the hydrohalic acids, like hydrofluoric acid or hydrogen fluoride. Their name changes depending on whether they're in their pure form or whether they're in aqueous solution. So for example, HF, which is hydrogen fluoride if it's in its pure gaseous form, is called hydrofluoric acid when it is in water. So when it's dissolved in water, it's hydrofluoric acid. Similarly, HCl is hydrogen chloride when it's in its gaseous form, its pure form. And when it's dissolved in water, it's called hydrochloric acid. The same is true for hydrogen bromide and hydrogen iodide. There are 2 different names for that molecule depending on whether it's in water, dissolved in water, or whether it's in its pure form, in these cases liquids. A few other incredibly common acids that you should just know their names of: carbonic acid, H2CO3, nitric acid, phosphoric acid, and sulfuric acid, H2SO4. So again, I would suggest that you make flashcards with the formula on one side and the name or names on the other side, and just practice both sides of those cards. It shouldn't take you but a few minutes to memorize these names. So you can't name molecules unless you have sort of the basic vocabulary down, just like you can't speak a language unless you have a set of nouns at your disposal. So you need to learn those words. So after you've got the words memorized, then it's time to practice sort of classifying molecules so you can identify which naming system that you need to use. And so I've sort of constructed a tree here that works for me, and I encourage you to construct your own tree based on what you've read and maybe what's in this video. The first thing to do, I'm teaching you today how to name binary inorganic molecules. The first thing you need to do is make sure you have one of those molecules. And so here's kind of what makes sense to me for how you can go about classifying to make sure you have one of those molecules and picking the naming system to use. The first thing to look for is, well, you can ask yourself if you have an acid. Acids are typically named with a hydrogen on the front of the name, and then the rest of the name follows. Sometimes there are multiple hydrogens, like sulfuric acid is H2SO4. It signals you that it's an acid. The common acids that I just showed you on the previous page, you should just know by memorizing them, and you just recognize their names. Other acids, which you don't know, you might recognize they're an acid because there'd be a hydrogen at the beginning of the formula. So if it's an acid, you use the acid naming system. If it's not an acid, then I would next check to see how many carbon atoms are in the molecule. If there's only one carbon atom in the molecule, it might be part of a polyatomic ion, and it could still be a binary inorganic molecule. But if there are many carbon atoms in the molecule, it's likely to be organic, and you will learn organic naming at another time. That's not this. It's not this naming system. So you should know that you don't have a naming system yet to deal with those unless you know organic naming. So if it's not a molecule that has a lot of carbon atoms in it, can you recognize that it's a binary molecule, meaning it has a cation and anion, two elements, one that's a cation and one that's an anion? Is it a cation and anion that are polyatomic ions, but two polyatomic ions together, or an element and a polyatomic ion together? So if it's just two, that makes it binary. If it's more than binary, then it has a different naming system. And you'll learn different naming systems in different courses. And so it's not for you to worry about now. So if the answer is yes, it's binary, the next thing you need to ask yourself is the compound molecular? Meaning, is this a compound that has sort of covalent bonding, or is this a compound that has ionic bonding? So molecular compounds have covalent bonding. Typically, we see molecular compounds when we have multiple nonmetals. So if we have more than one nonmetal bound, then that's a molecular compound. So if the answer is yes to the question, is it molecular, meaning are there two nonmetals? The binary compound is made up of two non-metal elements, then you would use the molecular naming system, which we'll talk about. If the answer is no, it's a binary compound, but it's not molecular, that means it's an ionic compound. And there are sort of two subtly different ionic compound naming systems for binary molecules. And the way we distinguish which ones to use is some of them have a cation that only has one possible oxidation state or one possible charge. And so I will show you that group of cations in just a minute. But the next thing you need to do is if it only has one possible ion charge, then you use an ionic naming system that has no Roman numerals to indicate the cation oxidation state. All other metals, they have multiple oxidation states, and you need to actually then indicate in the molecule with Roman numerals what the charge on the cation is. And so that is a slightly different naming system. So what I'm going to do now is we're going to talk about sort of these three systematic naming systems. The acid naming, you should just recognize it as an acid and already know the name just by memory. So if you're talking about a molecular compound, two nonmetals bound together, this is the naming system. You name the element that's further to the left on the periodic table appears first in the name. So you need to find that element and decide what its name is. You should know its name. Then you're going to put the number of both elements indicated with prefixes in front of the letter for that element, or the name for that element. And the prefixes are mono for 1, di for 2, tri for 3, tetra for 4, and so on, up to deca, and you can go higher than that, although you don't see it very often in binary compounds. If the first element or the first ion only appears once, it would have a mono prefix. You can just leave it off. It's assumed if it's a 1 in the first element, we don't say mono. It's not technically wrong, but it sounds weird when you put mono in front of the first element, so they're typically left off. And the ending of the second element is IDE. Remember, we looked at the elements in the periodic table, and we saw that all of them had IDE last names, and that would be sort of the name of the second element. So let's do a couple of examples. In this first example, it's a binary compound. It's a molecular compound because they're both nonmetals, nitrogen and iodine, right? We name the first element, which is nitrogen. It only appears once, so we don't need to put a mono, di, or tri outside of the front of its name as a prefix. And the second element is iodine. Because it's the second element, we want to include the ide name, so this becomes iodide. And there are 3 of them, so we would name it nitrogen triiodide. Nitrogen triiodide. That's the name of that compound. Another example is this compound. Again, the first element is nitrogen, and so its name is just nitrogen, the elemental name. But in this case, there are 2 of them, so we would say dinitrogen. And the second element is oxygen. It's the second element in the name, so it's going to get the IDE name. So it's going to be oxide, right? And there are 4 of them, so we would name it tetraoxide. Dinitrogen tetroxide, or tetraoxide. Okay, sometimes the A is dropped, so it could also be tetroxide. Dinitrogen tetraoxide or dinitrogen tetroxide. So those are both acceptable names for that compound using the molecular naming system. Again, these are molecular names because these compounds both involve 2 nonmetals as their binary constituents. When we're talking about ionic naming with no Roman numerals, these are the cases where the cation only occurs with 1 oxidation state, or in other words, with 1 charge. Cations of that type are the alkali metals, right? So the ones in column 1A of the periodic table, like lithium and sodium, they always have a +1 charge. The alkaline earth metals in the next row of the periodic table, like calcium and magnesium, those are called the alkaline earth metals, and they always have a +2 charge. There are a few special cases in other places in the periodic table of metals that only have 1 particular charge. So like silver, for example, only ever has a +1 charge. Aluminum only ever has a +3 charge. Cadmium only has a +2 charge, and zinc only has a +2 charge. So those are the cases in which we don't need to add Roman numerals because we already know what the charge on the cation is. So in these names, the cation is named first. So these are metals, so they'll be just given their elemental name. And then the anion name is listed second with ide on the ending if it's an element, or just with the polyatomic ion name. So no prefixes are needed or given because we know the charge on the cation. So for example, this compound has 2 constituents. It has lithium and it has sulfate. In order to do that, you actually had to know what sulfate is and what its name is for the polyatomic ion, right? And so the name of this compound would just be lithium sulfate. We don't need to indicate the number of lithium ions there because we know that sulfate has a -2 charge. In order for the compound to be neutral, there has to be 2 +1 charged lithium ions there. Let's do another example. In this compound, we have 2 constituents, in this case 2 elements. We've got aluminum and bromine, right? And so the name is just put together by naming the cation first. Aluminum, right? And we have bromide as the second ion, right? Bromine becomes bromide because it's an element and it's an anion. And just by saying aluminum bromide, we already know that there's one aluminum because it always has a +3 charge. There must be 3 bromides, right, in order to balance that charge and the whole compound be neutral. So these names don't need any prefixes. Okay? So that's ionic naming with no Roman numerals. Now, all the metals that aren't alkali metals, alkaline earth metals, or these special cases, they have multiple possible charge states. And so we use ionic naming with Roman numerals when we have cations that can occur in multiple possible oxidation numbers or have multiple possible charges. This naming system is very similar to naming ionic compounds that have a fixed cation charge, except we have to indicate parenthetically what the charge of the cation is, since it could be more than one thing. So the process goes very similarly. First you name the cation, and you indicate the charge now parenthetically using Roman numerals to indicate whether it's a +1, +2, +3, or 4, and so on charge. The next thing you need to do is you need to name the anion, and you use its IDE ending. If it's an element, or if it's a polyatomic ion, use the polyatomic ion name. So let's do a couple of examples just to sort of illustrate this. So in this example, we see that we have 2 elements, so it's a binary compound. We have iron and we have chlorine as the 2 elements. We know that chlorine is going to be listed second, so it's a chloride, and each chloride has a -1 charge. So there's a total of a -2 charge on the 2 chlorine atoms that are there, and that means that the iron must have a +2 charge, and so we would need to indicate iron 2 chloride as its name. Okay, and that we don't need to do a prefix on the chloride because it's clear from the charge on the iron how many chlorides are there. So let's do perhaps a slightly more complicated case. So this is also a binary compound. This time it's an element, which is the cation nickel, right? And sulfate, which is the anion, which is a polyatomic ion. So in order to do that process that I just did, I actually had to have internalized the names of the polyatomic ions and know something about the naming of cations that are elements, right? So that memory work is critical to get going in this process. Now to sort of figure out the charge on nickel, we have to do a little bit of thinking. We know that sulfate from our memory work has a -2 charge, and there are 3 of them, right? So the total charge here for the sulfate is -6. We know the whole compound has a neutral charge, and there are 2 nickel atoms, right? So that means this must be 2 times +3 charge on the nickel. So nickel must have a 3 oxidation number, a 3 charge. So we would write nickel, indicate 3 with Roman numerals, nickel 3, nickel 3 sulfate is the name of this compound, nickel 3 sulfate. We don't need to indicate the number of sulfates again because you can sort it out using the charge on the nickel. So there are a couple of other things I want to talk about before I leave this. First, we're going to be dealing with bases throughout this course. Bases are simply compounds that when added to water yield the hydroxide ion. So hydroxide is one of those ions that is on your polyatomic ion chart. It is OH with a minus charge. Okay, so that's hydroxide. And so they're named quite simply. You have a cation and you have a polyatomic ion, which is hydroxide. So this compound would be lithium hydroxide. So these compounds, they split apart when they're dissolved in water, and you get the lithium cation and the hydroxide separately. So it's considered a base because it yields hydroxide when dissolved in water. So there are many examples like sodium hydroxide, potassium hydroxide, magnesium hydroxide, calcium hydroxide. All of those compounds yield hydroxide when dissolved in water, and thus they're bases. There's one sort of edge case that I think it's important that you know about, and it might be a little bit confusing when you're classifying compounds, and that is there are very commonly hydrates of binary compounds. And the molecular formulas of hydrates always sort of indicate the number of waters that are attached to every molecule of the binary compound using this notation that is a dot, right? And so let's just talk quickly about how to name this compound. You always start by sort of naming the binary compound itself. So here, this is a binary compound. We have magnesium is the cation, and that's its name. And we have sulfate here. This is a compound which we would not have to use any indication of the charge on the metal because magnesium always has a +2 charge. So you would name it magnesium sulfate. Magnesium has a +2 charge, sulfate has a -2 charge. Together they're neutral. And magnesium sulfate, when it is made into a crystal in the presence of water, it forms a heptahydrate, meaning there are 7 hydrogens. So you would write heptahydrate. This is still considered a binary inorganic compound, even though it has, those extra waters on there. It's a binary inorganic compound that's been hydrated. So it's sort of grouped together with the binary compounds, and you should be able to name them. So far what we've been doing is we've been taking examples of names and converting them, or taking examples of molecular formulas and converting them into the name. It's important that you're able to go both directions with that process. And so here are a few examples of molecular formulas, and let's just sort of practice going back, some examples of names, and let's just practice going back to the molecular formulas. So this first compound is magnesium oxide, and so magnesium is an alkaline earth metal, and so we know that it's a cation and it's going to have a +2 charge. Oxide is the anion derived from oxygen, and it almost always has a -2 charge. And so this compound, magnesium oxide, is just MgO, magnesium oxide. So we worked from the formula down to the name. Here's another case. Again, we have magnesium as the cation in this name, and chloride now is the anion. Again, magnesium is an alkaline earth metal. It always has a charge of +2. We need to know that chloride is one of the halogens, and halogens adopt a -1 charge. And so we know that in order to have a stable compound magnesium chloride, there actually has to be twice as many chlorines as magnesium ions. So this would just be Mg magnesium Cl2, right? Magnesium chloride. We don't need to say dichloride because we know that magnesium always has a +2 charge, and thus we know we have to balance that with the chlorine, so there's no need in the name to indicate dichloride. That would be the formula from that name. Let's do one more that's slightly more complicated. Ammonium is the one polyatomic cation, and it's NH4 plus, right? And dichromate is Cr2O7 -2. So this is ammonium dichromate. And so we know that when this comes together in a compound, since the anion has a -2 charge, we're going to need to have 2 of the ammonium ions. Remember, they hang together as a group, so we would write NH4 parentheses and then 2 to indicate that there are 2 of them, and then we would show the dichromate ion. So that would be ammonium dichromate. So now you need to set about memorizing your ion names, and then practice converting names to molecular formulas and molecular formulas to names.